So good morning everyone. Today the experiment that we'll be performing is UV visible spectroscopy. Spectroscopy is the branch of chemistry which deals with the interaction of a matter with the electromagnetic spectrum. And the instrument that is used in this study is called spectrophotometer. It is a combination of spectrometer uh, that produces light and a photometer which measures that intensity of light which is produced by the spectrometer. Here in UV visible spectroscopy, which is also known as ultraviolet visible spectroscopy, absorption or transmission of the light that is produced by spectrometer is measured. The basic principle of UV visible spectroscopy is the measurement of absorption or transmission of the light in the UV and visible regions by the sample. When any light is passed through the sample, the electrons of the molecules present in that sample absorb energy from this light. And this absorption of energy causes an electronic transition in the molecule, because of which these electrons get excited and the transition of those electrons occurs from ground state to an excited state. And the energy difference between these two states corresponds to the energy of light absorbed, which is the UV visible region of the electromagnetic spectrum. Basically, in this experiment, the absorption or transmission is measured, and that measurement is used to determine the concentration of our desired substance in the sample. The law which is being followed in this experiment is Beer-Lambert's law, which was given by August Beer and Johann Heinrich Lambert. According to Beer-Lambert's law, the absorbance of a solution is directly proportional to the concentration of the absorbing species and the path length of the light passing through the sample. It means that the total absorbance of a solution, the total light absorbed by any solution, is directly proportional to the concentration of that absorbing species. The more the concentration will be there, the more the absorption will be there. So absorbance is equal to ECL. Here A is the measured absorbance, E is the E is the constant which is called molar absorptivity, and C is the concentration of the absorbing species. If we want to write it in the terms of intensity, then A is equal to log of I naught upon I, where I naught is the intensity of the incident light and I is the transmitted intensity. These are the basic instrumentation of the machine. First of all, there's a light source which produces UV and visible light. Then there's monochromator. It selects a specific wavelength that we'll be needing for our sample, and it only allows that specific wavelength to pass through it. Then there is sample container or cuvette, and finally there is detector. The UV spectrum is produced by the electrically exciting deuterium or hydrogen, and the sources of the visible light are that is used are tungsten filament lamp. Cuvettes are a small container that we use to keep our sample in it. For UV visible spectrum analysis, quartz or fused silica for UV visible spectrum analysis, quartz or fused silica cuvettes are used. For visible spectrum analysis, silicate glass or acrylic cuvettes are preferred. The cuvette size uh, is as follows. Most of them fit into a 1 centimeter square holder in the instrument. The detector measures the light intensity emitted by the cuvette, and it sends to a meter to record and show the values. This is the layout of a single beam spectrophotometer. First of all, there is a light source from which light falls on a collimator. Collimator is a The main function of a collimator is that it converges the light falling on it on a specific point. After this collimator converges all the light that is falling on it on a prism, and this this prism diverges those light rays on a wavelength selector. Wavelength selector here is a monochromator that we talked about earlier. After this monochromator, a specific wavelength of light falls on a sample solution, and from there, the light falls on the detector. That was single beam spectrophotometer, and this is the layout of the split beam spectrophotometer. The main difference between these two spectrophotometers is that in split beam spectrophotometer there is a beam splitter present, and in single beam spectrophotometer there is no beam splitter. In As you can see, in single beam spectrophotometer, all the light that falls on the wavelength selector falls on the sample solution, but in split beam, that light is splitted into two intensities. Intensity of the light falls on the reference, and the half of it falls on the sample. The reference that we use in split beam spectrophotometer is usually the solvent that we are using for the experiment. After falling on the reference and the sample, respectively, the light falls on the photodetector, and the data is then processed by the system, and then output is given. These are few applications of the DNA of UV spectrophotometer. There is an example given here of UV spectra of paracetamol tablets. Here we can show that we can clearly differentiate between the standard PCM, that is pure PCM, and the PCM with impurity. If the PCM is containing any kind of impurity, then there will be extra small peaks in the curves. There's a graph given here which clearly shows the difference between the peaks that is shown by 4-nitrophenol and 4-nitrophenolate. In this way, we can differentiate between whether the sample contains 4-nitrophenol or 4-nitrophenolate. These are the different peaks shown by the nucleic acids and proteins, sugar salts, and organic solvents. These are the few advantages of UV visible spectroscopy. The technique is non-destructive, that is, it allows a sample to be reused. It is a quick technique and allows easy integration into experimental protocols. It is quite easy to use, and the data that is produced by the system it requires minimal processing. And the instrument is usually inexpensive to acquire and operate. The sample that we'll be testing today is salicylic acid, and the solvent that will be used is 2-propanol. 2-propanol actually will be the co-solvent with the distilled water. The required apparatus is spectrophotometer, cuvette, test tubes, measuring balance, spatula, pipette, 100 ml flask, test tube rack, tissue papers. After preparing the salt, we'll be preparing different concentrations of the salicylic acid from the stock, and the concentrations will be 0.009, 0.01, 0.015, 0.02, 0.025, 0.03, and 0.035 milligrams per ml. Then after applying the dilution law, that is C1V1 is equal to C2V2, we'll be calculating the amount of stock that will be requiring for making each concentrations. After doing all the calculations, table will be prepared like this. After preparation of this table, standard curve for for all the concentrations will be plotted like this. A straight line will be acquired, and the equation that we'll be needing here is y is equal to mx. Here x is the concentration and y is the absorbance value. After plotting the standard graph, every group will be given a known concentration, and after using this standard graph, each group will be calculating the concentration of the unknown sample that will be given to them. Thank you so much.
This is the interface for this device. Okay, first we will do the wavelength scanning. So let me.
तो सबसे डाइल्यूटेड का क्यों लिए?
तो वाटर है ना,
अभी तो ब्लैंकिंग कर रहे हैं.
वाटर था.
हाँ,
अभी वाटर ही लोड हुआ है, वो बस लोड किया है वो. आई विल डू इट इन द नेक्स्ट फेज. ओके, सो क्लिक इन हियर. ओके, नॉट हियर, दिस वन.
सेट करें.
सो वी हैव
वेवलेंथ सेट. राइट क्लिक करो डिस्प्ले में. Setup.
see, I have took from 200 nanometer to 900 nanometer. So you see, it is from UV to visible, and IR also coming. So the instrument we can go up to 1100 nanometer also. Okay. So as we don't need that much IR region, so I am not doing that part. So okay.
ब्लैंक का क्यों कर रहे हैं लोग?
Blank.
का लैम्डा मैक्स क्यों निकाल रहे हैं?
अभी हम लैम्डा मैक्स तो नहीं निकल रहे. फर्स्ट वी आर डूइंग द, जब भी ये इंस्ट्रूमेंट यूज करना होता है, यू हैव फर्स्ट डू द ब्लैंकिंग. यू हैव टू मेक द कैलिब्रेशन. वंस इट इज डन, देन आई विल पुट द सैंपल एंड आई एम गोइंग टू चेक द लैम्डा मैक्स जो भी बोल रहे हो आप. अब पहले तो ब्लैंकिंग करना पड़ेगा. सो फॉर दैट रीजन मैं अभी ब्लैंकिंग कर रहा हूँ.
इससे ब्लैंकिंग होता है, हमने कभी देखा नहीं. पीसी कनेक्टिव.
जब भी स्पेक्ट्रोमीटर यूज करना होता है, यू हैव टू फर्स्ट डू द ब्लैंक. अगर आपको स्कैन भी करना है, वेवलेंथ स्कैन, देन ओनली यू परफॉर्म द स्कैन. ओके, तभी आपको वो पता चलेगा कि आपका जो कंपाउंड, अभी मैं अगर डायरेक्टली स्कैन कर दूं उसको डाल के, बट विल हैव द, इट विल शो द रॉन्ग एब्जॉर्बेंस बिकॉज यू आर नॉट नॉलिफाइंग द दैट सॉल्वेंट. यू आर डूइंग दिस ब्लैंकिंग टू मेक द इंस्ट्रूमेंट नो दिस इज माई सॉल्वेंट, एंड फॉर दिस जो भी जितना भी एब्जॉर्बेंस आएगा वो जीरो होगा मेरे. इंस्ट्रूमेंट विल नो, डोंट नो. इट्स means you have to like instruct the instrument, right? कि कैसे वो, उसको कैसे पता चलेगा कि ये आपका सॉल्वेंट, इसमें आपका क्या सॉल्वेंट है क्या नहीं है. फॉर दैट रीजन यू हैव टू डू द थिंग्स.
सर ये जो इसमें इतना क्यूबिट बॉक्स मतलब जो दिया है,
मल्टीपल एक साथ कर सकते हो, तो मूवमेंट करेगा उसके हिसाब से. अगर आपको 8 सैंपल है, अगर ये हमारे पास,
तो हम सारे भी डाल सकते हैं.
हाँ, अगर हमारे पास 6 क्यूबिट चाहिए उसके लिए आपको,
तो ये मल्टीपल में भी रह जाता है, लाइक कॉपीज में.
हाँ,
तो हमारे पास अभी नहीं है.
मल्टीपल बैटरीज
इतना सारा इंस्ट्रूमेंट्स है, सबके लिए एक पेज
इतना ज़्यादा है.
ऑब्वियसली
10 केबी जानते हो.
Okay, right? Blanking is done. If you want to see how this water will be, whether it will give you a peak or not, you can run it also. Okay. If I run it, it should be in the zero, right? Zero में ही आना चाहिए, right? Let's run this. I'll show it for the sake of this.
अभी उसको अभी वो जीरो हुआ.
अभी देखो, as I make it this water to make it blank, right? Zero calibrate के. So you should not get any peak. It will be a straight line, right? ये हो जाएगा पहले बार. Then I will go for your sample. Then we will see whether at what wavelength it will give you the peak.
At each wavelength, it will record the absorbance in the form of graph.
Yeah. In the form of graph also, and you will have this absorbance values over here. How to do manually?
वो जो
standard
1990 का स्पेक्ट्रोस्कोपी
1990 तो कहाँ पे?
एक्सेल में डेटा ले करके
इधर
graph
इधर ही
लिखे।
है डिपार्टमेंट.
डिपार्टमेंट 2010 को शुरू हुआ 1990 का कहाँ से
हाँ तो इसलिए तो खराब हो रहा है बार बार.
और जब फर्स्ट रन किए थे उसमें क्यों नहीं आया था
ये
सबको
उसमें
calibrate करें।
तो अभी क्या हो रहा है
अभी
कैलिब्रेट होकर
हाँ?
with respect to water ये again कर रहा है.
वाटर का ही करना
हाँ वही.
मतलब अभी इसको सैंपल के हिसाब से दिए
हाँ
Done? कुछ नहीं है peaks, right? Now you just load your sample. You just discard it. Load the next sample. इधर से ऐसे बनाना होगा. Okay. Let's run this.
सर ग्राफ दिखाइए सर.
ना sir. Answer.
बाप रे.
सैंपल लॉक तो नहीं रहा है ठीक
हाँ.
सर सॉल्यूटर जदी होगा एटा मैक्सिमम ये जो फास्ट जोटा देखेला पहले
ये
हमें
उसके बाद
0.03 वाला
वाला।
कंप्लीट सेतरे तो सी कंसंट्रेशन तो सॉल्यूट कम रही हो जीवो.
चल.
0.03 से उड़ कम ही तो रहेगा
नहीं वो कहया कथा हमें जो लैम्डा मैक्स टा फाइंड आउट करछे सॉल्यूटर तापरे
ତା ତମେ ଯେତେ କନସେଣ୍ଟ୍ରେସନ ନେଲେ ବି ସେଇ ପର୍ଟିକୁଲାର ୱେଭଲେନ୍ଥ ରେ ହିଁ ସେ ତାର ରେସ୍ପନ୍ସ ଟା ଦବ. ସେଇଟା ତ ତୁମକୁ ବୁଝେଇଲି କି ଆମେ ଫର୍ଷ୍ଟ we have to find out the at what wavelength the compound that you are mixing your solvent is means responding to the light. See wavelength 294
एक बार डिस्ट्रीब्यूटर करो
blank करे. Okay.
कनेक्ट तो हबो ना कनेक्ट हबो नहीं